Okay, so again, thank you all for coming. Today's speaker is going to be Ashley John. She is a third year in the electrical engineering department. Her advisor is Elahe Ahmadi. Today, she's going to be talking about MOCVD, grown aluminum silicate gate dielectric on gadolinium 3 oxide. So you can start whenever you're ready.
Thank you. Let me share my screen. Can you see my screen now?
Yes.
Thank you. So hello, everyone. Thanks for attending this PGSS. My name is Ashley Jen, and I'm the third year PhD student in Electrical and Computer Engineering Department. Today, I will present the work on metal organic chemical vapor deposition, grown aluminum silicon oxide gate dielectric on beta gamma oxide in 001 crystal orientation for high power applications. My research advisor is Elahe Ahmadi, and I would like to thank the funding agencies, Air Force Office of Scientific Research, National Science Foundation, and Office of Naval Research to support this work. This work was also performed in part at the University of Michigan Lurie Nano Fabrication Facility. So currently, many people use the information age to describe the age in which we are living. I would like to also call this age the power age, because a lot of questions in our society have to do with the power and energy. The need for efficient power generation, distribution, and delivery is quickly expanding in different sectors of industry, including transportation, industrial automation, and renewable energy. It is predicted that 80% electricity energy would pass through power electronics between generation and consumption by 2030. So power electronics is at the heart of this industrial revolution, which can be found in various applications ranging from data servers, electric vehicles, and motor servos in industrial robotics. In addition, we are facing an urgent need for new devices and technologies to manage the electric power in the 2 to 100 kilowatt voltage range, which is required in many advanced systems, including distributed grid systems, high-speed train, and energy-intensive industrial systems. So the power switch is one of the most important components in the power electronics. How does the power switch work? Here is the basic boost DC-DC converter circuits. We can see the converter means that it can change the voltage, either amplitude or the frequency from the input to the output. And for the ideal power switch, there are two states. One is the on state, one is the off state. For the on state, you can see as the switch here is on, it behaves like a shorted wire. So ideally, there should be no voltage drop on the power switch. And for the off state, this is like an open circuit, and the power switch should withhold the same or higher voltage than the input or output voltage. For the off state, because this is open, so ideally there should be no leakage current as well. So the current should be 0. And also for the transition time between on and off state, it should be instantaneous and should be immediately transferred to the on to off or off to on state. However, in reality, it is not like that. So for the on state, because we have some on resistance in the device, so the device will always show the voltage drop as shown here. And for the off state, when the device is withholding the high voltage, there is always the leakage non-zero current as shown here. For the switching time between on and off state, it is also non-zero, and although it is like only nanosecond, but it is also significant for the power loss. Talking of the power loss, It is a basic equation like the voltage times the current. So the total power loss equal to the on-state power loss plus the off-state power loss plus the switching power loss. For the on-state, in reality, because we have the voltage drop, so we have the power loss, the on-state current times the voltage. The same thing for the off-state, because we have the leakage current, the power loss is also significant. For the switching state, here, although the switching time is in nanosecond, but as you can see, both the current and voltage are much high. Like the current can go maybe up to 100 ampere and the voltage can go up to like 2 or even 100 kilowatts. So this is also a huge amount of power dissipation for the switching. And then for the traditional device, which is like a silicon-based devices, we have the drift region here to hold the off-state power voltage. Because silicon is the low bandgap material, so it has the breakdown field up to only 0.3 megawatt per centimeter. And the area here shows the voltage the silicon-based devices can hold. So, because voltage equal to the breakdown the field times the distance. So for this silicon device, for example, to hold the voltage up to 2 kilowatt, we need to increase the device dimension here up to right here to get the 2 kilowatt. However, if we adopt the wide bandgap materials such as gallium nitride or silicon carbide, because they have the higher bandgap, so they have the higher breakdown field. Also, we have the ultra wide bandgap material like beta gallium oxide. You can see it has the breakdown field of up to 8 megawatt per centimeter, which is around 20 to 30 times that of the silicon. So for the same voltage, like the same area for gallium oxide, it only requires the width of the drift region like this little. So for the gallium oxide based devices, it is much more compact than that of the silicon devices. We also have the relationship between the on-state resistance and the breakdown voltage. In this equation, the mu means the channel or the carrier mobility. EC is the breakdown field. If we plot this equation in the log scale, for different materials, we can see, for example, for the same breakdown voltage, compared to gallium arsenide, silicon-based devices give us higher on resistance, and this is not what we want because, as I mentioned just now, for the if the device has higher on resistance, it also has higher voltage drop during on state. The higher voltage drop gave us the higher power dissipation. So that means in this direction is like the device is performing better and better. Particularly for the beta gallium oxide, its performance is better than the silicon carbide and gallium nitride. These two are now commercially available for power switches in electric cars. You also may notice that the diamond is also better than the gallium oxide, but the diamond is facing some other issues for example, the high cost or it is very hard to achieve the growth of the high quality diamond field. So apart from the high breakdown voltage, high breakdown field, beta gallium oxide also has the following advantages for high power applications. First, it has monoclinic crystal structure as shown on the left. Also, the beta phase is thermodynamically most stable phase. Also, please notice that the melt growth of low-cost, large area, high-quality bulk substrate is available for beta gallium oxide. Right now, the commercially available substrate is around 4-inch. This is pretty good for this kind of material. Last but not least, the band engineering by alloying and heterostructures with other 3,6 group material, such as aluminum oxide, indium oxide is available for the band gap tuning. There are two device geometries for the power switches. The first is the lateral device and then the vertical device. If you are familiar with the MOSCAP, maybe in device physics course, this is just similar to the basic MOSCAP. If you didn't take that course, it is totally fine. I will just brief introduce it here. So for the MOSCAP, it has 3 terminals, which is the source, gate, and drain. Under the gate, there is the dielectric. Here it is shown as silicon oxide, and under the dielectric, there's gallium oxide. So the gate here is used to kind of generate carriers under the gate or turn this channel off. So when the channel is turned on, we have the carriers under the gate. And once the source is grounded and we apply the voltage on the drain, the carriers will move in this direction laterally from source to drain. So this is just the basic MOSFET. Additionally, for the power switch, we have to have the distance between gate and drain should be much longer because we want to hold the voltage between gate and drain for the off-state operation. The same thing, if you take a look at the vertical device, it is similar to the lateral, except that instead of putting the source, gate, and ground in one plane, now we put the drain at the bottom. So why do we do that? First, let me introduce the device physics again. So when the channel is turned on, the carriers move from source, like here, to the drain vertically. So it is why we call it vertical device. When the device is in the off state, the channel is turned off and then the voltage will be held between the gate and drain, mainly in this N- drift region. The similar thing is here for the, which we called FinFET, which is fin field effect transistor. So this is the cross section of the fin. It is very similar to this device. It is just that the gate is, instead of put on top, we are putting the gate on both sides of the fin to give us a better gate control. So the advantage of the vertical device is as following. First, we are utilizing the low-cost gallium oxide box substrate. Because if we want to grow some epi layer on the foreign substrate, we might suffer like the high density of the defects. But if we grow the N- gallium oxide directly on the N+ gallium oxide substrate, we will have fewer defects, and this leads to the lower leakage current. So this is the huge advantage of our gallium oxide-based devices. Also, this device has the capability of achieving high power density without enlarging the chip size. So as I mentioned, because the voltage is the equation, is the field time, the distance. So if we want to increasing the off-state voltage, we need to increase the distance between gate and drain. So if we do that in the lateral device, that means our device dimension is also increased. That is not what we want, and that will give us some high power loss in the high frequency operation. However, for the vertical device, instead of increasing the distance laterally, we can just increase the thickness of the drift region and to hold the high breakdown voltage. So this can be done without enlarging the chip size. Also, the vertical device has less surface sensitivity. So you can see the channel now is in the bulk, like away from the surface. It is very possible that we have some surface traps like along the surface of the material. So if our channel is away from that surface trap has less impact on our carriers. Last but not least, this kind of device gives us easier thermal management. So because when the device is operated like for a very long time, it generates heat. So for the vertical device, we can just put a heat sink like here, like on both sides of the device, and this thermal management is kind of like a 3D. But for the lateral device, all the carriers and channels are very close to the surface, and surface might be super hot and cause the reliability issues for the devices. So as you can see, for the both lateral and vertical device, the very important structure is the gate, the metal oxide and semiconductor, which we call it MOS structure. Especially for this dielectric, it is very important for the gallium oxide-based devices because gallium oxide is an ultra wide bandgap material of 4.9 electron volt. It is super hard to find available dielectrics for the gallium oxide. So the following work, I will focus on the dielectrics for the gallium oxide. As I mentioned, high quality dielectrics are important for enabling high performance beta gallium oxide FETs. There are several key metrics for dielectrics as following. For example, the high dielectric constant, large band offset, low interface state density, large breakdown field, and reliability. In particular, the interface state density is very important, which results in the variation in the gate modulation, the channel mobility, and the current collapse. As you can see here, if we have a surface interface states or surface states right here, the surface traps, if they kind of trap one electron on the surface, they behave like a negative charge. If they release the electron, they are like a positive charge. And we cannot control like when they release or capture the electron, which means for some traps, they capture the electron like at high frequency, but for some traps, they capture the electron even at DC. So it is, if there are a huge amount of the surface traps on the surface, this can give us the DC and RF dispersion, like for different frequency, the traps respond accordingly. As you can see for DC, the current is much smaller than that of the high frequency RF frequency. So for the aluminum silicon oxide, which is the alloying of aluminum oxide with silicon, has been proposed as a high-quality dielectric for GaN-based devices. Previous studies have shown that this aluminum silicon oxide has the potential to combine the merits of both silicon oxide and aluminum oxide. As following, like it can achieve the low density of the interface traps, the high conduction and valence band offset, and the high breakdown strength. For the conduction and valence band offset, as you can see in this figure, because we want to prevent any leakage current for the off-state operation. So this band offset here can prevent the electrons move from the semiconductor to the metal. If it can move, that means the conduction path forms and we will have the leakage current. If it cannot move, that if there is a barrier and this barrier is around maybe 20 to 30 nanometer, then this is like, we will have lower leakage current. The figure at the bottom shows the XRD spectra. And as you can see for aluminum oxide, which is the traditional dielectric for gallium oxide, and is now very popular for the gallium oxide devices, this aluminum oxide has the crystalline peaks as shown here. But for aluminum silicon oxide, if we dope the film with silicon, this curve is super smooth, which means that the suppression of aluminum oxide crystalline peaks has been achieved. This means our film is more amorphous with less grain boundaries and the dangling bonds. So consequently, we will have low interface state density. As shown here, this is the interface state density as a function of the energy away from the conduction band, EC minus E. This E is the energy distance away from this EC conduction band. We can see over the range of like from 0 to 2 electron volt, aluminum silicon oxide demonstrated lower density of state compared to that of aluminum oxide. So the promising result of aluminum silicon oxide for the GaN-based devices motivated us to expand its applications to the beta gallium oxide. In our work, we fabricated aluminum silicon oxide on beta gamma oxide. Using the MOSFET structure, we studied the electrical properties of this MOSFET structure. So the structure is shown as following: from the bottom to up, it contains the ohmic contact N plus gamma oxide substrate, which is 640 micron, and also HVPE grown N minus 10 micron epi layer, and then we use the MOSVD to deposit aluminum silicon oxide with different thicknesses of 10, 20, and 30 nanometer. Finally, the gate metal was patterned using lift-off process. The surface pretreatment prior to the aluminum silicon oxide deposition is contains either 3 cycles of UV ozone and HF or only HF to study the influence of the UV ozone clean on the interface state quality. The dielectric was deposited by the metal organic chemical vapor deposition. The growth condition is as following, and the silicon composition in the film is estimated to be 40%, characterized by the XPS. So the band gap, as shown here, the conduction band offset and the valence band offset of aluminum silicon oxide with respect to gallium oxide were estimated to be 7.3, 1.9, and 0.5 electron volts. So these 3 values are what we want for the dielectric on the gallium oxide. To study the impact of the UV ozone clean, 2 dual CV sweeps were conducted as following. So first, the MOSFET was biased from depletion to accumulation in the dark, and then held for a 10-minute electrical stress before sweeping back to depletion. During this 10-minute electrical stress, both the fast and slow traps are filled with electrons, and the slow traps, once filled with electrons, will remain occupied for the following CV sweeps. Then during the second CV dual sweep, the device was biased from depletion to accumulation without any electrical stress, and then biased back to the depletion. In this case, only the fast trap can respond. So we can see for the first CV dual sweep, the fast and slow traps can respond. The second one, only the fast trap can respond. So we can differentiate the fast and slow trap using these 2 dual CV sweeps. Then for the figure shown here, it shows the two CV curves. As I just mentioned, we can see the CV hysteresis for the samples treated by HF is much larger than the hysteresis for the samples treated by both ozone plus HF. The hysteresis show that yes, there's something happens due to the function of the fast and slow trap. So to calculate the density of the trap, we have this equation right here. The delta VB is the flat band voltage hysteresis, and the QT is the trap density. T is the dielectric constant, and Q is the electron charge, and here is just T is the dielectric thickness, sorry, and here is the dielectric constant. So the flat band voltage hysteresis can be calculated at the flat band capacitance. This chart compares the flat band voltage hysteresis and the calculated fast and slow trap density for 2 different samples. We can see for the sample treated with HF plus UV ozone, both the hysteresis and fast slow trap density are much smaller than that of the sample treated by pure HF. So this means for the HF and UV ozone, they might first oxidize the surface and then clean the surface contaminations very efficiently. To confirm that this equation is valid, we also fabricate the 3 different MOSFETs with different aluminum silicon oxide thickness, because this is a function of the dielectric thickness. You can see the linear fit shown here shows that yes, this equation is truly valid, and it passes across the origin. from the slope of this linear fit, we can get the trap density again. So to investigate the traps significantly below the conduction band right here, like we call it deep level trap, we adopted the deep UV assisted CV measurement. The methodology is done as following. First, the device was biased at accumulation for 10 minutes in dark. And right after this, we have a CV sweep swept from depletion to accumulation and is identified as a dark ideal curve. After that, the device was biased at depletion and illuminated by a 254 nanometer UV light for 1 minute. And then the device was continued to bias for at depletion for 10 minutes to let the generated holes move toward the interface and recombine with the trapped electrons. After that, immediately we have another CV sweep swept from the depletion to accumulation and is identified as post-UV curve. So as you can see, for after accumulation, all the traps are filled with electrons. So when we sweep the CV, which means that all the traps cannot respond with the voltage. But after the UV illumination, these traps are like the electrons recombine with the holes and the traps are empty. So the traps have the ability to capture the electrons. When they capture the electron, this has something different on our capacitance as measured here. So we can see for different voltage, the dark curve and the post-UV curve show us like the different capacitance. This show that yes, the trap truly did something in our MOSFET. And here is the equation to quantify that. The delta V is a function of both the interface state and also the bulk trap in the dielectric as shown here. They too can both trap the electron and change the capacitance during operation. And then we continue to kind of put this delta V into the other equation. And finally, we get this equation that the total trap density is a function of interface state density, the bulk trap density, and the dielectric thickness. And we fabricated 3 different devices with 10, 20, 30 nanometer dielectric. We can see from this linear from this linear fit, we can get the interface state density from the intercept, and the slope is related to the bulk trap density. So the result here shows that for our MOCVD grown aluminum silicon oxide, both the interface state density and bulk trap is much lower than the traditional atomic layer deposited aluminum oxide on beta gamma oxide. Using the same method, we also studied the impact of post-metallization annealing on the interface states and bulk traps. So as shown here, for the energy as a function of for the total trap density as a function of energy, the sample without annealing in this red curve is shown here. For the sample annealed at 350 degrees C is in this blue curve. It seems like after 350 degrees C annealing, we have larger interface states, which means the interface state kind of degraded after this high temperature annealing. However, in opposite, for the device annealed at 300 degrees C, we have the lower trap density over the energy range from 0 to 1.2 electron volt, which means that because for the MOCVD growth, typically we will have hydrogen in our films. So if we anneal the sample at some temperature in vacuum, it seems that the hydrogen can diffuse this into the air, which gives us the high quality of the film, resulting in this low interface states. We also characterize the breakdown voltage of our dielectric. So we apply the positive voltage on our gate metal the band diagram is shown here. So when we apply the positive gate voltage, most of the field will be held in this dielectric. And if we continue to increase the electric field or the voltage, we want to see at which point this dielectric breaks down. So as you can see, the red curve is the traditional atomic layer deposited aluminum oxide. In this black curve, and the green curve is the aluminum silicon oxide without annealing. We can see compared to aluminum silicon oxide demonstrated almost 2 orders of magnitude lower leakage current. And for this region, which is below the detection limit, we call it low leakage operation region. We can see for aluminum silicon oxide, it extended this low leakage operation region from 3.2 to 3.8 megawatt per centimeter. Also, if we further anneal aluminum silicon oxide, for example, for the 300 degrees C, it further extend the low leakage operation to 4 megawatt per centimeter. Also, the breakdown strength here, the device is breaking down. The breakdown strength was improved to around 8.2 megawatt per centimeter. This is higher than that of the underlying gallium oxide, like 8 megawatt per centimeter, which is super helpful for taking advantage of gallium oxide full potential for high power applications. Because when the gallium oxide based devices is operating, we want the breakdown happens in the semiconductor instead of like the premature breakdown happens in the dielectric. So if the breakdown field in the dielectric is higher than gallium oxide, it is what we required. And why, you might ask that why we want the leakage current so low or the low leakage operation region here extended, because as I mentioned before, the off-state power dissipation equal to the voltage times the current. So if the leakage current is very low, for the high voltage operation, like even up to 100 kilowatt, so we really want the leakage current as low as possible to achieve the low power dissipation. Furthermore, we studied the reliability of our devices by doing the CV step stress forward measurement. It is done as following. First, the device was biased from -15 to 2 watt as a reference curve, and then the device was held at a forward bias for 10 seconds before sweeping back to depletion. The forward bias here for 10 seconds was ranging from 2 watt to 15 watt. We conducted this measurement on 3 samples without annealing or annealing at different temperatures. Then we extracted the flat band voltage hysteresis for the 3 samples. We can see first, no significant change of the flat band voltage hysteresis between the not annealed and annealed samples was observed. We achieved like the flat band voltage hysteresis around 7 watt at the gate voltage around 15 watt. Please notice that here the maximum stress field of 5 megawatt per centimeter is 4 times that applied to gate in vertical gallium oxide FinFET on-state operation. Lastly, we also did the CV step stress reverse operations stability study. So it is shown as following. First, the device was biased from accumulation to depletion, and then held at different reverse bias for 10 minutes, and then swept back to accumulation. The reverse bias voltage was varied from -10 to -42 watt. We also extracted the flat band voltage hysteresis. So please note that for the samples annealed at 300 degrees C with higher breakdown voltage, which we demonstrated before, the CV sweeps of the sample here were also almost identical to each other. And the extracted flat band voltage hysteresis was stable for this sample until the reverse bias reaches minus 38 watt. But for the other two devices, it seems like some degradation really happened at higher reverse voltage. In summary, we have investigated the interface state density and the dielectric bulk trap in aluminum silicon oxide beta gamma oxide in 001 crystal orientation mask caps through different CV measurements. The CV hysteresis was suppressed by 3 cycles of UV ozone and HF dip. We achieved like the very record low interface state of 5.4 times 10 to the 11 in the MOCVD grown aluminum silicon oxide on beta gamma oxide by post-metallization annealing at 300 degrees C. Also, the breakdown strength was enhanced to 8.2 megavolt per centimeter. We also demonstrated a distinct improvement in reverse operational stability for our MOS caps. Yeah, thank you for your attention. I'm glad to take any questions.
Yes, thank you so much. That was a wonderful talk. And again, are there any questions for Ashley?
I have a question.
Yeah.
So in all of your stress testing, I was wondering how your device compares to the other devices that are in use now, like similar dielectrics.
For which parts? Thermal
sorry. So you've been testing, right? Doing stress testing for this beta gamma oxide, right?
Mm-hmm.
But earlier in the lab, you said that there were some other dielectrics that were, earlier in your presentation, you said there were some other dielectrics that were already starting to be used. So I was just wondering, like, how is this comparing to them in being actually applicable to use in the real world?
Yeah. So first, let's take a look. So first, for the interface state and the bulk trap, if we take a look at now the very popular like atomic layer deposited aluminum oxide, you can see it has higher or even twice interface state density and the bulk trap. Also, for the breakdown voltage, which we want our breakdown voltage as high as possible, because if we want to operate our device, for example, at 2 kilowatt, we want our breakdown voltage like maybe 4 kilowatt to just make sure we have enough margin. So as you can see, for atomic layer deposited aluminum oxide, its breakdown field is around 7.8 megawatt per centimeter, but for our device, our MOS cap is around like 8.2 or even higher for some random device on my samples. Also, the leakage current for our device is like twice, 2 order of magnitude lower than that of the other aluminum oxide films. Yeah.
Thank you.
Does it make sense? Okay, thank you.
Are there any other questions for Ashley?